Okay, hello guys. So we're gonna continue solving the Laplace equation. So we saw in the last video that you have a square metal, let's say like this, and you know the values of the of of the distribution on the boundaries. You can split that linear Laplace equation in the sum of four equations. Okay, that you will solve independently, and then you'll have the solutions. Okay, and then these will be the different values. Okay, uh, so the total thing will be split in four parts. So we're going to solve the last part. Okay, number U4. That is the hardest. Okay, because it has a trick we haven't solved. But otherwise all the other ones will be similar. One will be similar to this one that I'm going to do, and then the others will be just no. Should be the other ones shouldn't be problem. So we're going to solve number 4. So for number 4 we have the following. We have is on 0y. We have u4 equals g1 y, and on this side we have 0, on this side we have 0, on this side we have 0. Okay, and inside we have the Laplace equation equals to 0. Okay, this equation is also called potential equation. It's very important in electrodynamics. So as always, we start with separation of variables. So we obtain we look for a solution of the form x times y of y. And then once you start replacing in the equation, the second derivative with respect to x is just second parent of x times y of y, and the second derivative of u4 with respect to y is just x, second derivative of y, right? X times of x. So by the equation, if you move this to the other side, you move the derivative, second derivative of u4 dy squared, or second derivative of u4 with respect to y to the right hand side. You obtain this, right? So this is second derivative of u with respect to x equals minus the second derivative of u with respect to y, and then we have for one side we have a second derivative for x times y equals minus x times second derivative of y. So we do the as usual. We put x with x, y with y's, and then we got that this function is a whole function depending of a constant. So, my goodness, it's a whole function depending of only one variable, and then this other one is a function depending of only y. So this one depends only on x, and this one depends only on y, and they are equals all the time. So this is for all x and for all y. So the only way that this can be true is they are equal to a constant. So let's say the constant is lambda. So if I move my equations around, I will get a second derivative of x equals lambda x, and second derivative of y equals lambda y. So now we go for the conditions. So we have these conditions: u lambda y equals to 0, ux 0 equals to 0, ux h equals to 0. So when we plug in this over here, u l y equals to 0 is x of l times y of y equals to 0, and this is for all y, right? So since this is for all y, we don't y of y equals to 0, so that implies x of l equals to 0. Now we want ux0 equals to 0, and when after plugging in it, when using separation of variables, we have this for all x. So that means y0 equals to 0. And the last one we have x of x times y of h equals to 0, then we'll get y of h equals to 0, because this was true for all x. So in conclusion, I have two conditions and I have only one condition for x. So I have x of l equals to 0, and for this one I have y of 0 equals 0, and I have y of h equals to 0. So conclusion, which one is your store Liouville? X or y? Y. So this is my store Liouville problem. Okay. So this is the store Liouville problem, and lucky for us, this is the first case of the store Liouville problem that we have. What is it? Examples. So this is my case 1. So I have second derivative of a function equals minus lambda of the function, and the function at 0 is 0, the function at L is 0. So it turns out that the lambda ends are going to be n pi L squared. The eigenfunctions are going to be sine n pi x L. The function is going to look f of x, sine of n, well, in that case, this case, not going to be like that. Anyway, so let's go little by little. So we go here. So using a store Liouville problem, formulas for y, let's say, we get the following. So we said we get the lambda is gonna be n pi over what? Over h squared, right? We get y of y is gonna be sine n pi y over h, right? And this is for, because it's Fourier, is sine Fourier series is 1, 2, 3, and so on. Okay, so that's really good. So we have our y. So this is my y sub n, and this is my lambda sub n, right? So now I need to solve my second equation. I need to solve for this guy. So that guy. So let's solve. Let's say the equation 1, and then let's say equation 2. So let's say solving 2. Now solving 1. Now I had in some of your videos, people is so organized. So I'm sorry, I'm really not organized. So I have here that my solution for this. So this is a classical solution. We know this. So hopefully by memory. So there are two possible ways to write it down, and I'm gonna explain it since in wet work you might have a problem with wet work. So you can solve it. So you write the characteristic polynomial. So let's put it a second prime minus lambda x equals to 0. Okay. So you can solve it using the substitution x equal e to the mx. If you use the substitution, you will get m squared minus lambda equals to 0. When you put it here, you will get m equals plus minus square root of lambda, right? So you have this possibility. You can write the solution like c1 e to the minus square root of lambda x plus c2 e to the square root of lambda x. Or, this is an alternative, you can write it like s of x equals, let's say, another constant a cosine hyperbolic of square root of lambda x plus b sine hyperbolic of square lambda x. So it's a tradition to write this one, okay? Even if this one is right, usually people, for these partial differential equations, it looks more elegant to do it like that. So that's what people do. So that's my x of x. That's my solution for that one. And knowing that lambda is m pi h, so this is h, and this is h. So we'll get x of x equals a cosine hyperbolic of n pi x over h plus b sine hyperbolic n pi x over h. Okay, so that's how it goes. But then you try to, what we have the condition x of, oh sorry guys, it's not L. Oh, it's L or it's not L? Yeah, so we have the condition x of L equals to 0. So when you plug in, you're gonna see that you don't get too much, right? So you plug in x of L, this is 0, and then you'll get a cosine n pi L over h plus b sine hyperbolic n pi L over h, right? Cosine hyperbolic. And then this is gonna be not very productive. So this is not, we're not gonna do it like that, right? So since we can make the problem easier, and that was what I said, that tricky part. This is the tricky part. Choosing a different orthogonal basis. Okay, so here my basis, and you guys know this because you did homework. So my basis is cosine hyperbolic and sine hyperbolics. So here I'm gonna choose something different. I'm gonna choose the following. So you see how it goes. So we're gonna choose the solution x of x equals a cosine hyperbolic n pi h x minus L. I don't know why doing pi like an h. X minus L, and then plus b sine hyperbolic n pi h x minus L. Okay, so this one will be also a solution of the equation because it's just a translation. Okay, so this is gonna be also a solution, and you notice because we need to choose A and B such that satisfies the x of L equals 0. Okay, so that's the trick, guys. Okay, so we're gonna get, when we make h of L, x of L equals 0, things are gonna simplify. So I will have a cosine hyperbolic of L minus L is 0, so n pi h times 0 is 0, cosine hyperbolic of 0 is 1. Plus B, L minus L is 0, sine hyperbolic of 0 is 0. So you have A equals 0. So in conclusion, my solution looks like x of x is gonna be B sine hyperbolic of n pi h x minus L. Okay. So then let's call it x to the n of x. Since we have this n, we call it x to the n of x. So now we have y to the n of x, x to the n of x. So we're gonna now call the infinite superposition principle. Okay, so we had found u to the n of xy equals x to the n of x times y to the n of y, and this is sine hyperbolic n pi h x minus L. We can put the b. Let's put the b. Then it times y to the n of y. Y to the n of y is sine n pi h divided by n pi y divided by h. So this is sine n pi y divided by h. Okay. Okay, so oh, I should probably put this also this y to n, this b, let's put it, call it b to n. Okay, so my solution after superposition, so using the infinite superposition principle, so why? Because we already had used the following. We used this guy, we use this guy, we use this guy. So this equation satisfies all those, this one. However, we need to make sure we have that u0y equals g1 of y. We want to make sure we have u40y equals u1 g1 of y, right? So that's why we take the infinite superposition principle. So we're gonna make the sum, we're forcing it basically. Well, so when we choose u4 xy as the infinite sum of n equals 1 to infinity of x on x, y to the n of y equals to b Bn sine hyperbolic n pi over h x minus L times sine n pi y over h. Okay, so now when you plug in here at x0, so you get you need to make sure you are getting something, right? So when you plug in here at 0, you get sum of n equals 1 to infinity Bn sine hyperbolic n pi minus L, so let's put minus L over h. Okay, so so that's how our equation is gonna look. This is gonna be our solution. So our solution is gonna look like that. Oh, Bn and then times sine n pi y over h. Okay. But now notice that this guy is a Fourier series, right? This guy is a Fourier series because these guys are constants. This is a sub n for a Fourier series. So to solve this problem, we need that this g can be solved as a Fourier sine series. Okay, so separation of variables is like let you work, and at some point it gives you the conditions for in order in the process you see what conditions you need to put in the g's to find a solution. Okay, in this case we need to put here that g can be expressed as a sine Fourier series, and better than that, we have a formula for a sub n, right? Because we know how this a sub n looks like, right? So a sub n looks, you guys know this by memory now, right? Hopefully me too. So a sub n has to be integral between 0 and h of 2 over h. So this a sub n g1 of y sine of n pi y h dy. Okay, and this a sub n is Bn. Oh, sorry. This is a sub n, right? But a sub n is Bn times sine hyperbolic minus n pi L over h. Right? But therefore, I have a formula for B sub n. So B sub n, I can move this one down. I'm gonna move this one down. So B sub n is really sine hyperbolic minus n pi L over h times h, and this is my B sub n. Oh my, is that my, I call it B sub n. Yeah, that's correct. So my B sub n is coming from Fourier series. So that's my solution. So This is sine hyperbolic n pi or n pi h, not pi, pi x minus L, and the b sub n is given by this formula. Okay, guys. So, so one more example, and this is very useful in physics. Students from physics always tell me, I wish I was taking this class before, because in the electrodynamic class, that is an advanced undergraduate class, it's one of the last physics they see. Uh, uh, I don't know if the last one, but it's probably one of the best. And they see all this really fast. Okay, so uh, people in physics do this one of the hard classes to take. Okay, guys. So this is here we stop.